Hi, you guys. My name is Mallory. I am a soil TA on Fridays, and I am not getting a invitation to work, so I'm using my phone. So I hope this is useful. We're going to do some erosion math. Yeah, let's give this a try. Ooh. Nice. All right, I hope you guys can read that. So the question is, you have a 10-acre farm and you lose 1 inch of soil in a huge storm. The density of the soil that was lost is 70 pounds per cubic foot. How much soil did you lose? So the first thing we want to do is identify what it is that we're looking for. So you guys know the equation, right? That D equals M over V. And that means that density equals mass over volume. But one of the things I like to do is kind of identify, like, what does this actually mean in layman's terms, right? Like, if you were going to describe what mass and volume are to people who don't know what mass and volume are, that kind of looks something like how much stuff is in a space, any given space, really, right? So I can say that I have a backpack in my car, right? So that's some stuff and some space. I can also say that I have a backpack plus last weekend's gym bag plus empty coffee mugs plus some change, right? And that's all in my car as well. And so the latter would be more dense than the former because I have more stuff in the same amount of space when I have my backpack and a gym bag and all that other stuff versus just my backpack in a car. So that's kind of what density is talking about, how much stuff is in a space. So when we think about what it is that we have here, I always like to look at what information is given, and then that kind of helps you determine what it is that you're maybe even looking for. So we know we have 10 acres, right? And an acre is some length times some width, right? An acre is therefore equal to some area. So we have 10 acres. And then we have 1 inch of soil that we lose from a huge storm. And that soil is going to represent like a height or a depth or a thickness, whatever one you want to think about. I like to think about it as depth because when we draw this picture, right, okay, so we have some kind of area. And we have some kind of depth, or we have some kind of thickness. The only thing you don't want to do is call it D for depth because that can get you confused with density. So I'm just going to write out depth, right? And the depth is 1 inch, right? 1 inch, right there. And we have our area, which is our length. Area equals length times width, and our area is also equal to 10 acres. So on this diagram, we'd have a length, width, and a depth, right? All these. And our length and width is equal to 10 acres, and our depth is equal to 1 inch. So when you look at that, I mean, that's pretty characteristic of a volume, right? You have length times width times depth equals volume. So let me write that out for you guys. Right? And if we're going to multiply these things out, length times width times depth, to get a volume, we need to get them in the same units, because if you multiply an inch by an acre, like if we were to multiply this together, we'd get 10 acre inches. And that doesn't really make any sense. So we want to try to find a kind of a common unit so that we can multiply all of these together to form a volume. And so we'll do that by saying, like acre, let's see, we'll say that 10 acres times 43560. Right? So we'll say that 10 acres is what we have. But we know that in 1 acre, 43560 feet squared are in that acre, right? So we have 43,560 feet squared in 1 acre. So that equals the length and the width of 1 acre. But we have 10, so we'll multiply it by 10 acres, right? But that only gives us feet, and we kind of want to go to inches here because that's what our depth is in. So we'll go one step further, and we'll say that in 1 foot, there are 12 inches, right? Now again, we want to get to just inches. And so if we look at what our units say, we have acres that are canceling out, and we have feet that are really close to canceling out. But if we multiply this, we'll end up still with 1 inch times 1 foot, because only 1 foot is going to cancel out of these feet squared. So what we're going to do is we're going to square this entire term. And that's essentially saying we have 10 acres times 43,560 feet squared in 1 acre times 12 inches times 12 inches per foot. Right. And when we do this, we get, let's write it all out again. I always like to write all my steps just because it really keeps me on track. So don't feel like you've got to start doing calculations here. Write it all out if it makes more sense to you that way. So we have 10 acres again, right? Times is 4,356 feet squared. And by the way, I'm not sure if I already mentioned this, but this term here, this 43,560 feet squared per acre, this is just a unit of conversion, and this is going to be given to you on any exam or quiz or anything like that that you might have. I got this from Tony. You can get this from Google. This is just a conversion, right? We're just trying to get 2 inches from feet and find a common unit between acres and between inches, and so we do that through going through feet. So when we multiply this out, 12 times 12, 1 times 1, inches times inches, feet times feet, we're going to get 144 inches squared over 1 foot squared, right? And that's because whenever you are multiplying anything out, you guys, you always have to multiply your units by each other as well. That's part of unit analysis, and if you haven't done a bunch of that in chemistry classes, this is really the time to get good at this, because it's really going to help lead you to figure out where it is that you might be going wrong, or how to kind of point you in the direction of the right answer. If your units work out, a lot of times your answer will. Not always, but it's a really great tool to use. Is unit analysis, right? So I know I need to get feet squared to cancel with feet squared, and so I'm going to multiply this out so that I can do that. So in the process, so now I can actually do some math here and get an answer for at least how many acres or how many inches are in 10 acres. So I'll start by canceling my units, right, just to make sure I'm on the right track, and it looks like they all cancel except for inches squared, which is okay because we want a length times a width, and so we're going to have our units inches times inches, so the inches squared makes a lot of sense. And so when we do that, when we actually multiply all this out, and you can check me in a calculator, we get 62,726,400 inches squared. It's a lot of inches in 10 acres. So that means, right, just so that we're double checking to make sure we understand actually like what this means, that means that this 10 acres is the same thing as saying 62,726,400 inches squared, right? Which is why we use something big like an acre to represent that type of area. But it's an area nonetheless. It's inches squared, and this acres is feet squared, 43,560 feet squared. Great. So now that we have an area, remember we have an area, we don't quite have our volume yet, but we're close. Because we know that our volume is again equal to length times width times a depth. And we've just found in inches what our length times width is, what our area is, right? Which is 62,720, or 62,726,400 inches squared times our depth, right? Which is just 1 inch. So when we multiply this out, again, it's really important to write in all of your units, because when we write this out, our volume is going to be inches cubed, right? Because this giant number times 1 is just that number, but an inches squared times an inch is going to be an inch cubed. And that's a great thing, because volume should be in units of something times something times something, a length times a width times a depth. I know I'm repeating a lot of stuff here, but I just want to make sure that we're all on the same page when it comes to what volume is, what mass is, what density is. So cool. So now that is our volume, right? That equals our volume. So we're like halfway there. Now we need to think about the fact that we are given a density. And that density was given as 70 pounds per cubic foot. And so this is where things get a little bit tricky. Well, I mean, really the only tricks in here are unit conversions. And so we're going to really just do that again. So we have our volume. We know our density was given, and density will generally be given to you guys in one form or another. So now we got to figure out how to find some kind of common unit between density and between volume. And looking right off the back, I see feet cubed and I see inches cubed. And we know that there are 12 inches in a foot. So I'm going to go and just roll with that for a second. So we have 70 pounds per cubic foot. And we know that in 1 foot, we have 12 inches. Right? So again, I want to cancel, I don't want to be left with pounds per feet squared per inch if I just cancel the 1. So I actually want to multiply this by itself 3 times. So give it a cube, right? So that's essentially the same thing as 70 pounds feet cubed times 1 foot over 12 inches times 1 foot over 12 inches times 1 foot over 12 inches. So when we cube something, we don't just multiply by 3. We actually have to multiply 1 foot times 1 foot times 1 foot, and 12 inches times 12 inches times 12 inches. And again, always a good idea to write in your units, because that is what's going to kind of clue you into the fact that now we have feet cubed up on this side. So 70 pounds per cubic foot. And so 1 foot times 1 foot times 1 foot, oh, tongue twister, is 1 foot cubed. And when we do 12 inches times 12 inches times 12 inches, we get 1728 inches cubed. You can check my math. If it's wrong, I apologize. I did it on my phone. So, and I can't use my phone because you guys are using my phone to record this. So anyway, when we multiply this out, so now it looks like we can start canceling some stuff. So we have a foot cubed, we have our cubic foot, and another cubic foot, and those things can cancel. So now we can finally get something in inches that matches our volume. So by following the units, we'll do 70 pounds divided by 1,728 cubic inches, and that's going to give us a density of 0.0405 pounds per cubic inch. So essentially what this is saying is if you have a cube, right? I tried to draw a cube for my lab this morning and it wasn't very good, and this one isn't very good either. I don't even know if you guys can see that. My cube. There we go. So in 1 cubic inch, right, these are inches. 1 inch. An inch by an inch by an inch. Length times width times height or depth, whichever one you want to choose. Thickness, all the same. It's going to weigh, and weigh I use loosely if you're an engineer, but for the rest of us, it's going to weigh 0.0405 pounds. So that's how much mass it actually has on this planet. I say on this planet again if you're an engineer and you care about the weight force. But for the rest of us, again, not a big deal. That's the mass of this cubic inch, 0.0405 pounds. Cool, so we're almost ready because now we have our volume, which is this giant number. I'm going to write it out one more time because why not? Always write with the units. And we have our density, which is 0. Right? And we're solving for mass. And we know that mass equals volume times density. And we know that, again, because if we do some simple algebra up here, right, to solve for mass, we just multiply that volume times density to equal mass. Right? Great. So let's do that. And when we do that, we get, actually I'll do it on the other page so we can see how the units cancel out. Try to be upright for you guys. There we go. So we have mass equals volume times density. So mass, and what did we just say our volume was? Times isn't that just beautiful? We can cancel our units. We end up with something that makes sense for mass, which is the pound here. And so when we multiply this out, we end up with a mass of 2,541,000 pounds. So that's how much soil you lost in that storm, right, over your 10-acre field if you lose 1 uniform inch. I do want to do just a really quick demo because this looks, right, like you look at all this and you're like, oh my gosh, Mallory, that is so much stuff I've got to figure out. So many calculations I have to do. But I want to show you why it's actually much, much easier than you think, and this stuff should not keep you up at night. And the way I'm going to show you is by using the metric system. So I am employed through Paul Stoy, who is in charge of the Biosphere-Atmosphere Interactions Lab, and all of the stuff that we do is, I spend most of my life converting, and I told my Friday lab this, I spend most of my life converting weird imperial units to the metric system, and I spend a lot of my life doing that for a reason, because the metric system is just absolutely so beautiful. And I hope you come to see that at some point or another in your life, at some point in your mathematics career. I hope you find some beauty in the metric system because it is absolutely stunning. And I'm going to start with a really easy, or I'm actually going to finish with a really easy example. So let's just pretend we have 1 cubic centimeter. I think the reason we a lot of times get wigged out with the metric system is because a lot of us can't really conceptualize what a meter is compared to a foot. And the whole, I hope that doesn't trip you up because it doesn't really matter, right? Like, let's just take off our imperial hats and cross the border into Canada and put on our metric system hats and pretend that we don't even care what a meter looks like or feels like. Just pretend we have no understanding of what a meter is, right? But we know that there's this weird thing called the centimeter, and we have 1 cubic centimeter, right? And again, this is a thickness, this is a depth, this is a height, whatever you want to call this. Something times a length times a width is a volume. So for our instance here, we've got 1 centimeter times 1 centimeter times 1 centimeter equals 1 cubic centimeter, right? So that's our volume. And if I tell you that the density of this cube is 1 gram per centimeter cubed, right? This is a mass over volume. A gram is a unit of mass. A centimeter cubed is a unit of volume, which we have here. And I say, what's the mass of that cube? We're going to use our handy-dandy equation that we just used, density times volume, right? To say that, okay, cool, well, the density of that cube is 1 gram per cubic centimeter, and the volume of that cube is 1 cubic centimeter. So when we cross out our units, we just get the mass of this cubic centimeter as 1 gram. And you guys might look at this and say, oh my gosh, we're never going to get an example like that on a test. No, you're not going to get an example just like this on the test. But what I want to tell you is that every single erosion math problem is this problem. If you notice, the only thing that we did differently, right, is use unit conversions to get acres to work out with inches. If Tony gives you millimeters, then we're going to use, we're going to convert millimeters maybe to inches, maybe to feet. All we're doing is unit conversions. That's why this entire question looks incredibly lengthy, because we're just trying to convert between units, which, by the way, are all going to be given for you. So they're all right there. You just need to know how to use those tools. But truly, 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 every erosion problem is this problem. You have a density that Tony's going to give you, almost always. You have a volume. If you have a farm and it's lost some soil, you have a volume. You have an area over which you had soil, and you have some depth of soil that you lost. That's a volume of soil, right? And that's going to give you a mass, always, every time, 100%. So I think Tony talks about the Holy Trinity of, right, where you have density equals mass over volume, and mass then equals density times volume. And I mean, all of these, it's just doing some basic algebra to get to what you need. So the first step, again, I want to emphasize, just let's go over it one more time. The first step in the problem, every time, always, is to say, what do I have and where am I going? And in class, I also liken this to tree skiing, right? It helps to know where you want to go before you get there. And those of you who have taken calculus or will be taking calculus will have realized that or will realize that. If you think of your limits, it helps to know, like, pattern recognition, where you want to go and how you want to get there. So we know we have 10 acres. We know we have an inch. Already I go, oh, look, an area, a depth, that's a volume. So we have volume. And then we're given density. So immediately I know we're solving for mass in this problem. And the only tricky thing is figuring out how to make 70 pounds per cubic foot kind of coincide with something that you can compare with inches and acres. And so that's all that we did here, is we took acres, we made them into cubic, or into inches squared, which is an area, and then we multiplied by that 1 inch to get a volume. And then we took the density that was given, and we created, instead of pounds per cubic foot, we took that and we made it pounds per cubic inch. And then, and then we solved for mass. That's all we did. again, the same thing that we would do if we had some cubic centimeter. Which, by the way, this density, 1 gram per cubic centimeter, is the density of water, which is why I use that. It's just a common, just something I know. So go with what you know. I hope this was helpful. Please come see me, my office hours. If you have any other questions or you want to go over any other problems, my office hours are Wednesday from 10 to noon. Even if you're not my student, I'm more than happy to help. Or go see your TA. They are all well-versed on Erosion Math, and if you're looking for Tony, try Taco Monte's, because that is like 9 times out of 10 where he is. So again, hope this was helpful, and good luck on the practicum next Friday. Study this stuff. Come to the, I think we have a Sunday study session. Read the stuff that's online. And yeah, good luck, you guys. I hope this was helpful. Have a great rest of your weekend.